Good morning, everyone. It is my pleasure to introduce today's speaker, Dr. Adrian Cristal, from the most famous supercomputing center, Barcelona Supercomputing Center. You don't have a picture of your supercomputer handy? No. So they have a supercomputer that is placed inside a decommissioned church. It has a glass cube built around it, and it sits where the pews were.
Very impressive.
Very impressive indeed. So it's not the fastest, but it's the most beautiful one, right? So Dr. Cristal received his PhD from the Polytechnical University of Catalonia in Barcelona, and then he worked at the university there as a professor, and then he finally became a pure researcher. He doesn't have to teach anymore. He just supervises PhD students from the Supercomputing Center. He's an expert in computer architecture, and he will tell us about his recent work in architectures for the edge and machine learning.
Okay. Thank you, Alex. First thing, now you go to discover why I'm not teaching. Okay, I'm going to talk about this work, the BiSon-e, lightweight high-performance accelerator for narrow integer linear algebra computing on the edge. Very large title. This work was mostly, of course, of my PhD student, Enrico. We do very few things. He was doing almost, I will say, 99% of the job. So I go to start. First, the context definition. This is more or less the outline. We can start with the context. First thing that we have, that we want edge processor require high performance while respecting the type power and area constraints. This is something that is true for one side, but I will say that historically for us was a little different. I think that Enrico comes saying, I have a good idea where we can apply. So at the end we say, okay, in order to sell this, we need to find a place to sell. So we decide to sell to the edge processors. So we go to have many applications, deep learning, cryptography, stream matching, that will run in the edge. And they have to compute linear algebra style, we can say, kernels, but using narrow integers. So we have two options actually for doing that, currently to do that. One is a general purpose processors that are not optimized for a narrow integer. We are talking about narrow integer, something that is less than 8 bits. So if this is narrow, because if we don't have the definition, maybe 8 bits is too narrow, but no, we are thinking something 1, 2, 3, 4, 5, 6, 7, up to 8. Or we can do an application-specific accelerator. But sometimes for the edge that we are looking for a very little processors, having an accelerator specific for that maybe is too large area. So what we want to do is to use in this BiSon-e that it go to gap, will be in between these two things. Will be more efficient than a vector processor. And if we compare the area that we go to add in the processor, it's about 600 times less than the area of the vector processor. Of course, the vector processor can do many other things that we cannot do. But for a narrow integers, if you are thinking to do only narrow integer and adding this, is too much area. And it's more flexible than application specific. Okay, what is binary segmentation? This is our, we can say, technique that we go to start to use. Binary technique is a technique that what we go to do is to, one second, I have my pen here. Okay, binary segmentation is a technique that we go to pack many narrow values in one register. We go to do usual operations, like addition, multiplications, and using this, we go to get the value that we want. Example, very simple example. Assuming that you want to pack 2-bit elements and you want to do a lot of additions of 2-bit elements. What do you need to do? You need to do these 2 bits plus adding a 0, having 3 bits elements, doing this many times with one value and another value you do in the same way. You add these things, and you have at the end the addition, the 2-bit addition, only doing one addition. But we can do more things, not only addition. We can do addition, subtraction, reduction, inner product, that is what we go to talk, outer product, linear convolution, Gress common division, discrete Fourier. This technique started in the 70s. Okay. So in order to do binary segmentation, we need to represent the number. In the representation of the number, we go to have, we have to have on one side, this the vector, so this will be the value. We go to have the little values, that is the numbers that we want to represent, 2 bits, 3 bits. And we go to have some, we can say, size that we want. So we want to put 2 bits and maybe 4 bits, depending on the operation that you want to do, how many bits you need to pad. And according if you are using integer negative numbers or positive numbers, only positive numbers, you do a different way of padding, but usually what we do is something like this. We will be having some difference, but the basic is this one. So we have a vector that we have a lot of elements that we want to pad. Each one we multiply, and we at the end having ending a register of 64 bits or 32 bits. And the clustering width is the bit of the values, and the clustering is the number of total bits that you go to represent one number. If CBW is equal B, we can do this to packing, assuming that you have a 2-bit element and a 64-bit register. We can pack there up to 32 2-bit elements. This is good for compression, but if we want to operate, we need to have this value CW larger. This allows us to operate and recover the correct value at the end. If you have any question, please, you can interrupt me, no problem. Okay, let's do an example. This is inner product. We go to do the inner product between 7.5 and 4.2. First step is packing these values. So we go to have, in this case, there's a formula here that say the CW has to be the number of bits of the first element, the number of bits of the second element, plus the logarithmic of the size of the vector. In this case, this is 7. So the 7, for example, we add here. We add 4 bits here on zeros, and we add the 3 ones. Here we do the same, 4 bits of zeros, and the 5, the same thing in each place. So we transform this number to this number, and we transform this number to this number. We do now a multiplication. And at the end, what we need to do is to extract this value that we have here, and we go to have the inner product between these two values. If we go to do linear convolution, it's a little more complex, but it's more or less the same thing. We have here the formula in order to calculate how much bits we need to add. We can say these things. We do the multiplication of these. And now we can split this. And we go to have these 4 values that the linear convolution of these 2 values. The linear convolution, you can see here how this is expressed. You go to do the first one will be the 3 multiplied by 1. And after you go to do the 1 multiplied by the 1 multiplied by 1 and the 3 multiplied by 2, if I don't remember bad. You can continue so on in this way. So we are like moving this over these numbers. Okay. What happens if we try to use binary segmentation in a general purpose processor? It is possible? Of course it's possible. But we're going to have a lot of overhead. First thing, this enables to having like SIMD-style computations on a scalar pipeline, because at the end we go to use only one operation that is a normal operation and a scalar LLU that you go to have. So we don't need to add any, we can say, hardware or any special hardware for doing this. For doing inner product or linear convolution, if we are using 7 bits, 32 bits register, we can pack up to 2 7-bit operations or 6 1-bit operations. So this means that we can do a computation of 2 values or 6 values, depending on the size of the element. If we have 64 bits, we can go to up to 2 15 bits or 10 1-bit operations we can represent. So in one vector, in order to operate, we need to add up to 10 1-bit elements. We need to add these zeros at the beginning. Or if we are in 15-bit operations, we can do only 2. Here you can see how this works. We can see that for 32 bits, we have this number. So for 1, you have 6. For 2, you have 4. This has to be 7, by the way. OK. No, 6, 1. It's OK. And this is how this is working. OK, what is this? So when we do this computation at the end, we are saving, because we go to do only one multiplication and we go to get everything. We are saving for 3 to 19 less arithmetic operations. So we do one operation, and we have in total, if we are doing 1 bit, 19 less operations. For linear convolution, even if better, we have to 2.5 to 90. OK, what is the issue that we have with these things? We have here what we are doing. What are the operations? We have 3 operations in order to do this inner product. One is the extract, and then the other is the pack, and we do the multiplication. So the extract, here the packing first, and the multiplication here. We can see that most of the time, what we are spending the time is in the packing operations. In the linear convolution, we have something different, because we are having 4 operations, but the most important one is the extract operation. So, but at the end, what happens if we are trying to implement this in a normal processor? At the end, we don't go to win almost nothing. Sometimes we go to win, sometimes not. So what we want to do? What we know is that the binary segmentation offers a lot of improvement, potentially, we can say. But these improvements we cannot achieve because we don't have the instruction set support and the functional extension in order to do that. What we go to add is, of course, an instruction set in order to be able to exploit the binary segmentation in the full potential with a very few instructions, and we go to do only for computing the inner product and linear convolution. We go to add some hardware unit that efficiently performs the pack and extract vector operations, and this is not an accelerator, so we can use for many different things. It's integrating the main processor pipeline. Right? I think that is an advantage. OK, this is the, we can say, the architecture that we have. This is what we add. This is our accelerator. And what we have is a certain kind of configuration ways to do this. We can configure the extension, or we can extend, and we can configure the packing. In fact, in the packing, there's more things here, but we can configure more or less for every one of these numbers. We can do the same thing here. What means that? We can have, for example, here, the input data can be 8 values of 8 elements. So we have 64 bits with 8 elements of 8 bits each one. So we fill the 64 bits that we have. Or we can have 7, and in this case, we can have in total 9 elements in the 64 bits. So when we go to use this accelerator, we expect to have in the data in this way. So at the end, these values are transformed in something that it will be 21 bits internally. This will be internally here in the. We'll be having 3 values of 21 bits in order to operate. And we go to have 3 of them. So we change from this representation to few of them. And when we go to process these values, we need to do 3, we can say, 3 iterations. Because at the end, if we want to process 8 elements, but we have in total, we divide internally in 2 vectors, each one on 3 vectors, one of 3, another 3, another of 2, we need to do 3 iterations in order to do the computation. And we need only one element for post-processing. When we are doing the packing, that usually the packing, if you have this kind of application, assuming a neural network, and you want to have the weights, we go to do only once. We are not doing this in every iteration. Usually you go to pack many of these operations only one, and after you go to use packet directly. So we can pack 8 bits. This is the input, and we go to pack in 64, 1 bit 64, or we can have a 2 bit 32 or 4 bit 36, or we have also the other number that we have here. And when we are doing the packing, we have only one stage in the pre-processing, and 8, 2, 4 is depending on the size, how many you go to have. What are the instructions that we have? We have very few instructions, in total 5 instructions. One is to set up the configuration, the BSC set. That what we go to do is giving this information to the hardware. We did only once, and after we can start to use the hardware. We have the BS pack in order to pack in operations. And we have 1 operation for the inner product and 2 operations for the linear convolution. Because the size is like when we are doing any multiplication that we extend the number of bits. So we have one part for the low bits and the other for the high bits. So we need to do 2 operations. In the other case, because the inner product, we get some subset of bits, but these bits are in a, we can say, good place in the first element. So we don't need the second one. So how this works? Assuming that we go to use the BS IP, we go to starting having 2 elements, that the 2 elements are equal. We can say, for example, this element that are the 5 bits width. So we have in total 12 elements. So this will be transformed internally in element of 64. So we go to having here, we go to this unit. And in this unit, we go to have, from this element that is 5 bits, 12 elements, we go to extend and we go to create internally certain registers, IC0 and IC1. One is from the source 1 and the other for the source 2. This is sending to the multiplier. The multiplier returns this value. We have the mask unit, and we can do here the extraction of the bits that we want. So it's a very simple circuit. Okay, and this is for when we do the control of the things, for the BSC set. So the circuit is very simple. It's not a complex circuit, and it's a very simple way to work. So when we do in this way, we are having in this one, we need to do 3 times calling this operation. Okay, we do an experimental evaluation. First thing, we implement BiSon-E in Gen 5. This is one thing that we do. We are doing this in order scalar processor. The idea is to doing this for edge computing, so we are talking about very little processor. And we are using 2 cases of study, quantized convolution neural network and LC-based approximate string matching. We go to compare this with a Gen 5-based RISC-V BPU that also we develop in-house. So it's also a very simple RISC-V vector processor. Has only 2 lines, so we'll say 128 bits vector processor. We estimate the power consumption using MacPath. And also we integrate this in a scalar in order processor in order to evaluate the timing and the area that we spend. And we compare also with the RISC-V BPU that we have implemented in the same processor. The vector processor unit is in the same. First thing, we go to have an execution time of the inner product and the linear convolution. First, we have a naive implementation, that is what you do in software. And also we have a binary segmentation with a 64-bit RISC-V instruction set, or using maybe a better implementation with some bit manipulation instruction, and with what we are proposing, that the BiSon. If we here see, we have here for 1, 2, 4, and 8 bits. For the inner product, we are having here what are the speed up that we get here. If you see these speed ups are larger than the speed up that we are having, where is these ones? I have to add these things at some point. Okay. If you can see here that we was having that the arithmetic intensity was 19, and at the end we are getting more. Sorry for going in this way. And here, for example, we have 22x. This is because we are starting using the packet instructions. So we do this outside, and after we have more speed up because also we are reducing the memory footprint. So, and also if we compare, we can have the naive here. We have here the RISC-V. Here, if we have bit manipulation instructions, and here we have the BiSon-E. The same, something similar happened when we are talking with the linear convolution. Even we have sometimes better performance than in the inner product. Okay, we do also experimental evaluation using convolutional network. We are using 2 of them, AlexNet and BGG16, I don't remember bad. This is what happened in each of the layers. So we have the layer here, and we can see how is the BPU in this case. We are using the BPU in order to compare, and we have the BiSon with a 2, 8, 4, and 2 bits. We can see that in some of the, for example here, that 4-bit, more or less, if we are in a 4-bit here, so this is a BiSon-E with 4-bit, is more or less the same speed that we can get with the 2 lanes BPU. For this is more or less the same, and if we see the energy, we go to see that our energy always is much lower because we have a very, very little hardware that we are adding. So this is a scalar, and here, sorry, this is the energy that we need to look for. That is, that we are having a very good energy footprint in any case. With the BCC, it's a little difference. Here, the equivalent to the BPU will be in 2 bits, and otherwise, we have a better energy efficiency compared to the BPU in all the configurations. When we do the approximate string matching, we can see also that we have, according to the text, we have that is going down. But in any case, we have a very good speed up, and also the vector processor unit has a good speed up. This is for 4-bit alphabet, and this is for 8-bit alphabet. So we are more or less between 22 to 61 faster, and we are maybe between 1.3 to 3.2 faster than the BPU. And we always show better energy efficiency than the BPU. The last thing that we do was integrating these things in the in-house SoC. We are running the synthesis and place and route in 65 and 22 nanometers. Good point is that we are not adding any critical paths in our design, so the speed is exactly, the frequency is exactly the same. What we notice that the area that we go to use for the BiSon-e, that is this area, comparing to the area of the BPU, is 600 less. And the power consumption is 0.04%, so it's nothing. So what we can say at the end is that we can implement this in a very efficient way and having very low cost. Okay, what are the conclusions? We can use BiSon-e in order to optimize narrow precision linear algebra computations. These achieve good performance and, of course, save memory space. We can do from 2.5 to 90 times, reducing the complexity, arithmetic complexity, and we can have a comparable performance than a BPU. It has a very low area and power overheads, and only few instructions in order to use. And this can be added to any general purpose architecture, so I think that it's easy to implement in different, we can say, algorithms. Okay, that's it. Half hour, it's okay. Any question?
There is no mic today. Mic is not working, so speak up if you want to ask a question.
No questions. Okay, great. There's one, sorry.
So you mentioned in a conclusion slide that it seems to be possible to extend it to some other architectures. But I noticed that on your on all your implementations, like both in the simulator and in the physical SoC, you're only mentioning in-order processors. Would it be like much harder? I'm not saying impossible, I don't know, but maybe it would be much harder to implement it for the out of order.
I don't think so. At the end, you can see this like any addition to the integer LLU. And at the end, what happened with the recovery mechanism will be exactly the same. You have some input register, some output register, like an addition, like any other operation. So what happened is, assuming that you have a misbranch prediction, the value of the original register will be recovered. We are even not having any kind of, we are even not producing any kind of exception here. We don't have any hazard, we can say. So adding this in an out of order, I don't think that will be very difficult or go to imply anything complex to do. The point that we are thinking is that for IoT kind of processor, that most of them are in-order processor. For this reason, we don't test it. Yes?
Do you have compiler support for the additional instructions?
No. No. We are a computer architecture team, so we have to talk with the compiler group. The only issue that we have in the BSc is not like here that you have the two Alex that are very friendly. We are not very friendly with the compiler people. So sometimes happen these things. So no, the compiler people are very good at the BSc, so I don't. But they pass, and we are going for our pass. And if we go to say, okay, please do something for this, they go to say, no, I don't have money. I have to do my own project, so forget it.
You have to pay them, in other words.
Yes. If we get money and we pay them, they go to do that.
So I wanted to ask you, what is the latency of your unit? How long do these instructions take in the execute stage, let's say?
First, it's pipeline, and I think that was 3 cycles, more or less. I'm not sure about this, but was in this, because we have, okay. We have 1 cycle at the beginning, and after we need to send to multiply. The multiplication takes what the multiplication takes, because they use the multiplication unit that you have. If you have someone that is 2 cycles, 2 cycles, 5 cycles will be 5 cycles. And after we have the last stage that also is 1 cycle.
So packing is 1 cycle?
Yes. At the end, packing is like shifting some things, and it's not a...
But variable lengths shift.
Yes, it's variable length. But it's not having all the lengths. You have something that you can set up at the beginning. Maybe it was, I need to check it because I don't remember exactly. Maybe it's 2 cycles, but
that's close enough.
Yes, but it was not too many cycles.
And then the processor, the SoC that you were showing, that's a RISC-V processor.
Yes, a RISC-V that we developed in some of the project, and we add these things here.
We had a talk by Mikel Moretto.
Yes, about this processor. It's the same processors that we use, the Sargantana one. We are now doing a lot of processors there. So, by the way, if someone wants to come to work at BSc, at this point, it's a very good moment because there's a lot of projects and a lot of money, so it's very easy to get in. Sorry, but I have to do some publicity here.
But do you mean after graduation or before graduation?
This is something that if some people wants to do, I don't know, 1 semester, something like this, we have some scholarship now that is called Severo Ochoa that has several, we can say, calls, I don't know, 2 or 3 per year, and we can use this in order to found people in order to be 3 months there.
Okay. Can I come?
Alex, you always can. So no, but we can use, and this can be used for undergraduate people. So if someone wants, please contact us, and we will to be very happy. Sorry for that we want to steal students. Or doing PhD, master, everything is possible there.
Okay. On that note, are there any other questions or comments or anything? No? Okay. Well, in that case, you got lucky. You're leaving early today.
Sorry, fast usually.
Yeah, well, Adrian is in the